So this is going to be my first video on quantum mechanics. We are just going to deal with concepts that I introduced in classical mechanics and looked at them. Then we will take the eyes of quantum mechanics and look at them in a new way, simply. So let's start with force, which is mainly the most important thing. It's like the heart of classical mechanics. It explains every single thing, basically starting from push, pull to, friction, which is basically an opposing force, but it is simply a force. Centripetal force, its reaction, every single thing around us, which we, don't really experience, which don't really notice, is a force. It's just cancelled by numerous amount of forces acting around you. You are right now are being acted upon forces, which is quite a dumb way of saying it, but it is like everywhere around you. And the reason why you're balanced sitting on your table right now is you're literally balanced by numerous amount of forces canceling each other. So now I'm not going to talk about classical physics the whole time, but I'm going to give a glimpse at the end of this video. But I'm going to start with quantum mechanics at first, which is actually which we actually not consider force in quantum mechanics. We actually consider something else. We actually have an intuition that force is directly related to energy. So in order to start watching this video, you should have, or it is recommended to have a background in physics, mainly college physics, college level physics. Or if you're watching this video from the South Asian countries, then you should have 9th or 10th grade physics. Or if you want to go deep down, you should have 11th or 12th grade physics as well. So when quantum mechanics, force is directly related to energy. And energy is basically the heart of quantum mechanics. So we are not going to study the math of quantum mechanics in this video, but we are going to do some, classical physics math, which I'm going to show you in a calculus way as well. So it's like an intuition to have, in quantum mechanics. Everything is quantum mechanics is abstract. You have to have an intuition about it, which is quite a hard thing to do. But once you get it, it's fine. Well, and once you get it, it's not that hard to have an intuition, So let's start with kinetic energy. So let's stop it here and let's start with energy. So every single thing, even an electron or proton, contains energy, as we know. And that energy, which in turn relates to frequency, energy is directly proportional to frequency. The higher the frequency, as in the higher the frequency, the higher the energy. The higher the frequency, the higher the electron vibrates on a specific pattern. So let's talk about kinetic energy. When you're moving, you're actually doubling your kinetic energy, because the velocity in kinetic energy is literally squared. So when you increase your velocity 2 times, you have to your kinetic energy increases 4 times, which happens because so we're literally making an assumption that energy increases over kinetic energy. So So we are making an assumption over here. We are making an assumption over here. If you run in a straight line, let's neglect friction and let's neglect any sort of resistance on that particle, right? Doesn't that actually mean your frequency should also increase because your energy, as in your kinetic energy, is increasing? So this is where the abstract thought comes in, because you have to think about we are running in a straight line and we are bouncing on a frequency as well. That doesn't actually make sense, but it does actually, because if you go to a quantum state, if you increase your microscopic level, right, you're actually going to see some weird behavior of particles which don't actually exhibit a classical behavior. The whole thing literally changes. And let's make sure that we understand this. If you're an electron and your energy is directly related to your frequency, which means that how fast an electron is vibrating, that's simply explaining how fast an electron is, how high the frequency of that electron is. When we touch something hot or something cold, for example, this is hot, right? This table right here, if this table is hot right now, so if you touch it, you feel that it's hot. What does it actually mean? It means that the electrons of that atom, of that table, are generally higher in generally contain like higher kinetic energy, and the atom will have an increased frequency compared to a table that's not that hot, right? So if you apply a force of this box, it starts moving. So if the box is moving, it has some kind of kinetic energy, which increases the energy of the electron, which vibrate or dance at the higher frequency. You have to have an intuition of quantum mechanics, which doesn't actually apply to bigger objects, but if we increase your microscopic nature, then you have to have an understanding how quantum system works. So we will get to all that and the math part later in the videos, but right now let's take it a bit slow. So I'm just going to explain some ideas of force in classical physics so that so everyone is not that confused about how a force in classical physics works. So this is basically Newton's second law, and this is force equals mass and acceleration. Mass is simply constant in classical physics, but in quantum physics, it's actually not constant, because according to Einstein's relativity theory, mass increases with energy. And how does energy increase? It increases velocity. And how does velocity increase? If you apply a force to something. So it's actually everything, every single thing, the main concepts: velocity, mass, energy, frequency. All that is literally related to. They're all related directly. And so back to Einstein's relativity equation. If you increase the mass in a classical in a classical system, the mass remains constant. But if you increase the mass of a quantum system, the mass actually increases to a certain instant, and after that it's constant. So it's basically a logistic equation. It's not that beautiful on my tab, but it works okay. It works okay. So an infinite mass does not exist. So if we increase the mass, if we increase the velocity, which increase the mass in a quantum system, the mass is going to increase on a certain instant. The mass will not going to go to infinity, because that's just not possible. The mass does increase by very little instant. That is why light does not have infinite mass. Light has no mass. And so I'm going to write this equation again. So the acceleration will be we can write acceleration as dv over dt, which is simply the rate of velocity over time, or a certain amount of time, and this will give us a differential equation. Does this mean so then you're gonna know the acceleration is simply how fast the body's velocity, how fast the body's velocity is increasing over time. So if a body has an acceleration of 2 meters per second squared, then its velocity increasing by 2 meters per second each second. For example, if a body is moving from mean position 0 seconds reaches to 1 second, velocity is 2 meters per second. At 2 seconds pass by, its velocity is 4 meters per second. 3 seconds pass by, its velocity is 6 meters per second, so on and so forth, right? So this is basically how your acceleration works, and that is going to be it for this video. This was force in quantum physics, and that was basically the most basic thing you can learn about quantum physics. Right, I'll see you in the next video.